Good morning, everyone. The first lecture should have raised a few questions in your minds, and so I'm going to answer some of those now, and some of them will be answered in the next section. In particular, let me just say real quickly that one thing I did, which might have raised a question, actually should have, is when I had this. I had the derivative of the temperature with respect to time was equal to, that is, the rate of change of the temperature with respect to time of the pizza pan is proportional to the difference in the temperature and the temperature of the room. So I had that. And then what did we do? We brought this, we called it separation of variables, and we brought this t minus beta underneath there, and we brought the dt up here, and we proceeded to find the antiderivative of both sides. And that should have raised a question in your mind. Wait a second. This thing is not a fraction. It's not like something like 3/4. It's its own symbol. The change in temperature, the derivative of the temperature with respect to time. And how can you take that thing and just break it up into two pieces and think of it as a fraction? And the answer I'll give you more fully in the next lecture, because I'll show you that why this system works. In fact, when we got the answer, remember the answer was this. It was a e to the kt plus beta was the answer. Anytime you want to check to see whether you actually have the answer or not, all you have to do is plug it back into this differential equation and see if it works. In fact, as long as I have it there, let's go ahead and do it. What does this say? I'm claiming that this thing right here is the solution of this differential equation. So to be a solution means that it has to satisfy this equation. So let's go ahead and do it. What does this say? It says if I take the derivative of this thing, okay, well, so if I take the derivative, I'm going to get the derivative of this side is equal to, let's see, what's the derivative? Any constant just stays where it is. And then the derivative of e to anything is e to that thing using the chain rule times the derivative of this thing, which is going to be a k. And then the derivative of a constant, of course, is 0. So that's what this side gives you. And now if you take this side, what do we get? Well, let's see. First of all, it says to take k and to multiply it by t minus beta. So if I take this thing and subtract beta, notice what I'm going to get. I'm going to just get this right here. And so that's what that gives us. And notice that gives us the same thing. I could have done all this on the first lecture, but it was getting kind of long already. So anyway, this is, and also I forgot, so to be honest with you. But anyway, this shows that, that this is indeed a solution, in fact, the solution of this differential equation. And that's all you have to do whenever you want to check to see whether something is just plug it in and see if it satisfies it. So my point is that this system that we used, even though it may lead to questions, how could you break this thing up the way you did, it led to getting the right answer. And so it does seem to work. We'll show why it works in the next section and give the theory behind it. But anyway, wanted to point that out. So there's a couple things to notice. And then what next? What next? Let's go ahead and define some of these words that I've already been using. And so I'm going to look at my notes here as we go. First of all, a differential equation. I'm always going to abbreviate differential equation as just DE. Even here I will, because it's in context, that's the only thing it could ever mean. So a differential equation is just an equation which includes the derivatives of a function. Okay? An equation containing some, at least one, let's just say at least one derivative of a function. Okay? And it could be any of the derivatives. So here's some examples. We already had one example, oops, that I just showed you. Here's another example. I'll write it as dy your variable in this course is either going to be x or t. That's typically what it always is. You use a t if you think of the variable, independent variable, as being time. You put an x there if you think of it as being some sort of a distance or position. So just to get you used to various things, let's write this dy dx. So dy dx is equal to 3y. Okay? There's a differential equation. dy dx is equal to 3y, and it might be that you can figure out the solution of this particular one without even having had any theory. You just think, what is a function whose derivative is 3 times the original function? So there are various things you could try. Again, I'll suggest that you try it on your own before and push pause and see if you can figure it out on your own before I tell you. But now I'm going to assume you've done that, and so I'm going to give you the answer. The one that works, and we'll see, get into more of this theory later, is just y of x is equal to, I'll just say, 5 times e to the 3x. See that? That works. Because if I take the derivative of this, what am I going to get? dy dx is equal to 5 e to the 3x, and then you have to multiply by 3. 3 times 5 is 15. So there it is. So sure enough, the derivative is 3 times the original. So there's an example of one. Let's try another one. How about dy dx is equal to 3x? Notice that's very different. It looks similar, but it's totally different. This is 3 times the function. This is 3 times the variable. So this is one you already know how to do, okay? All you need is the antiderivative of that. So what's if the derivative of y is this, that means that y is equal to what? You add 1 to the power, divide by it, you're going to get 3 halves x squared, and then plus some sort of constant. Agreed? So actually, back in Calc 1, when you were finding antiderivatives, you were actually doing differential equations there. You were finding solutions where all you had was the derivative and you didn't have the function involved itself. All you had was the variable. But anyway, there's another one. Let's try another one. And again, the book contains a lot more examples. I'm not going to try to be comprehensive here, but let's try another one. How about I'm going to use different notation here. I'm going to use y double prime plus, let's say 9y is equal to 0. There's a rather important one. Differential equation. Can you think of one that would satisfy that? So what's that saying? It's saying that if you take the second derivative of the function and add 9 times the function to it, you're going to get 0 there. Anything there comes to mind? Another way of writing that, of course, is to say that y double prime is equal to negative 9 times y, like that. And you could play around with things like e to the x, e to the 3x, and so on, and see once what works. And I won't go through all the possibilities, but again, the more you kind of play with it and try it on your own, the more you'll kind of just discover and learn and become familiar with it. So I encourage you to keep doing that. Here's the answer, though. Again, this one might come to mind. You think, well, let's see. By the time you take the second derivative, you end up with the negative of the function. Let's pretend that 9 wasn't there. Can you think of what would satisfy that? What would satisfy this? By the time you take the second derivative, you end up with the negative of the function. There's two functions that satisfy that. It's the sine and the cosine. Because if you take the derivative of the sine, you get cosine, and when you take the derivative of the cosine, you get the negative sine. So you get a negative there. And if you start with the cosine, then you get a negative the first time. So either way, you end up with a negative by the time you take the second derivative. And so the one that's going to work here is going to be something like this. Y, let's use x again. Y of x is equal to 3 times the sine of x. I'm sorry, not 3 times the sine of x. Sine of 3 times x. And again, we're going to learn how to do all this stuff later on. I'm just giving you examples here. So let's check it out. Here's a function. If I take the first derivative, what do we get? Y prime is going to be 3 cosine of 3x. Agreed? And then the second derivative is going to be what? The 3 stays where it is. The derivative of the cosine is the negative sine, so it's going to be negative sine of 3x, and then you have to multiply by the 3, and when you multiply by the 3, sure enough, you end up with a negative 9 there. So look at there. Sure enough, the second derivative is negative 9 times the one you started with. Do you agree that we would have gotten a similar result if we would have started with cosine of 3x? If we would have done that, we would have ended up with the same thing. And then if you're really thinking, you might realize, maybe I could put those two together. So in fact, the most general solution, and again, I don't want to scare any of you off because it's all stuff we're going to be talking about later, but I just want to point out that the most general solution to this problem is something like this. A sine of 3x plus b, two constants there, cosine of 3x. If you start with that and take the second derivative, those all just stay where they are, and you end up with a negative 9 in front of that, and you end up with a negative 9 in front of that, and you end up with negative 9 times the thing that you started with. So there's another example of a differential equation. So there's all sorts of them, and so enough said about that. What are some other important words? And again, let me just follow my notes here. The next important word is ordinary. Ordinary. DE. Everything we do in this text is going to be an ordinary differential equation. The ones that are not ordinary, the modifier is called partial, a partial differential equation. A partial differential equation you get when you have a function of two variables. So for example, if you want the motion of a guitar string and you want to know what's the position of this guitar string, then the position is going to depend both on the point along the x-axis here, and it's also going to depend on the time because this thing is moving up and down. So there's a function of two variables, and kind of a nice problem that maybe we'll do this semester later on is to show how we can get the differential equation which models the position of a guitar string. And when you have that, then you're interested in the derivatives with respect to x and with respect to t. And so instead of dp dx, which is the derivative with respect to x, if p is a function of two variables, you use this sort of notation instead. You put a little, it's really its own symbol. It's not a Greek symbol at all. It just means the partial. And so you get that sort of thing when you have a function of two variables and you want to take the derivative with respect to one of them. So that's called a partial differential equation. We won't be doing any of that unless I just want to show you this particular problem. Otherwise, we won't be doing any of that this semester at all. And so everything that we have will be functions of just one variable. just one variable, and so those are called ordinary differential equations. Okay, so function of one variable. Okay, what's the next term I want to give you? Order. The order of a DE is simply the highest derivative that you see. So for example, if I had the third derivative of y plus 7y double prime of x, and you don't have to put these x's in there if you don't want to, minus x cubed, or x to the fifth, let's say, times y prime of x is equal to 3y of x. Okay, just to have something like that. Okay, so there's a differential equation, and you notice the highest derivative that we have is the third derivative, and so that would be a third order differential equation. Okay, it's just the highest derivative that you find. By the way, if you get something beyond 3, you start getting too many ticks. If you go 4 ticks and so on. So then sometimes some authors use Roman numerals like this, and some authors just put a little 4 in parentheses like this to indicate it. But we won't have much use for anything beyond, in this course, much beyond the second order differential equations. So there you go. That's the order. So I'll just say highest derivative. Okay? Linear. There's an important word. Linear DE. Here's an example of a linear DE. X to the fifth times y, I'll make this a third order again, y triple prime plus sine of x times y double prime of x plus e to the 3x squared times y prime of x is equal to 7 over the ln of x. Okay, something which is pretty weird. Okay, that's a linear DE, and the reason it's linear, let me just put a y of x in there as well. Well, in fact, here, let me do this as well. Plus ln of x times y of x is equal to 17. I'll just say is equal to 17. Okay? So that's an example of a linear DE. And the reason it's linear is because it doesn't matter what crazy things we do with a variable. Look at here. We took the sine of it. We have this. We could make this over x cubed right there. Let's go ahead and make that even worse. Here you have an exponential. Here you have this whole thing, all that. You can do whatever you want with the variable, but notice that the function itself, we did nothing fancy with it. It just sits there, y prime, y double prime, y triple prime. And by the way, you don't need to have them all in there. You could either leave this one out. That's all fine too. Okay. Anyway, those are all called linear DEs. You can do whatever you want with the variable, but the function itself just sits there without changing it at all. As soon as you do anything to this, so if we had 1 over y here, 1 over y of x, or if this were the square root of this thing, or do anything to this thing at all, take e to the y or anything like that, then it's no longer linear. Okay, then it's no longer linear. So to be linear, the y's and all the derivatives have to just sit there without having anything done to them at all. It's just like that. And the question is, why do we call that linear? We'll get into the theory of that and give a fuller explanation later on, but think of it in terms of an equation of a line. The equation of a line is just something like this. There's the equation of a line in the plane, and notice this could be any sort of messy number you wanted. This could be a pi, this could be e, the ln of e, or not the ln of e, well, ln of e is just 1. Let's make this the ln of pi, make that pretty weird, plus 1 over e to the square root of 2 times y is equal to 1 plus the square root of 5 over 2. That's the golden ratio. Okay, so that's just a line. Okay, let me make sure that you're all with me here yet. My computer blanks out on me, and oops, yep, very good. Okay, so that would be a line, right? That would be a line. You could find the slope of it, and you could find the y-intercept of it. The point is, as long as x and y are just there, you can make these as messy as you want, and you still have some sort of a line which looks like that. As soon as you do anything with this, though, right, write it as 1 over x, or write this as y squared, then you no longer have a line. You're going to have a parabola, or you're going to have a hyperbola, or something else. A circle, you'll have something else. So it's similar to that. So these are like the variables here. You leave them alone, but you can make the things in front of them as messy as you want. Okay, so that's linear. Homogeneous. Homogeneous, as far as I've ever seen, you only even apply that word to linear differential equations. I don't think there's any real reason to apply it to others. I'm speaking off the cuff though, so I won't say for sure. But typically, this is something that's only used with linear DEs. And all it means is that when you take all the derivatives and the function and you put them on this side, here's your y right there, and you set it equal to something, the thing on this side has just got to be 0. Okay? That's all it means is to be homogeneous, is that here's all your derivatives, here's your y, they're all on this side, it's all set equal to 0. As soon as you set it equal to anything other than 0, t squared, or x squared I should say, or 5 or 7 or whatever, it's non-homogeneous. Okay, so homogeneous just means that the I'll just say set equal to 0. Okay. And then separable. So this is the one I mentioned yesterday, or I should say in the first lecture. First lecture was a separable differential equation. A separable DE is one, I'll just say, can be written as some function dy is equal to some function dx. Okay, it can be written like that. You can that's what we did in the problem yesterday. We got all the capital T's over here, and we got all the small t's over here. This one didn't have any small t's. This one didn't have any capital T's. So you could separate the variables. See that? And as soon as you do that, then you can just integrate each side, find the antiderivative of each side, and you're good to go. Okay? So those are very important. They're important for two reasons. They're important because we have a way to solve them, and they're important because there are a lot of things in the natural world which can be written as a separable DE. So we'll be spending, several lectures solving lots of problems that are separable. Okay? See once if there's any others. No, that's basically it. So those are all the words. Let me just do a couple of problems from the book. So this is going to be a little bit of an incentive for those who are taking the course from the book, and maybe will be motivated to watch these if they are going to get some free answers. And for the rest of you, if you come and get the book, you'll be able to have some solutions as well. So here's problem from the book. Here's what it says. It says, given 2x squared times y double prime plus 3x y prime minus y is equal to 0, determine if the following are solutions. And I've got three different possibilities. Y is equal to the square root of x, y is equal to 1 over x, and y is equal to x squared. Okay, so we'll do this problem just to kind of re-emphasize how you can determine if something is indeed a solution. So notice, by the way, that this is an example of a second order DE. It's also a linear DE because you're not doing anything fancy with the function and its derivatives. It's also a homogeneous second order linear differential equation, right? So all those things apply to this. So let's just check each of these and see if it works. So square root of x, in order to do that, we have to, I'm going to first of all write that as x to the 1/2 power. And so now let's take the derivative. I'm going to write y prime is equal to what? 1/2 x to the minus 1/2 power. And then y double prime is going to be what? You bring this down, you're going to get what? Minus 1/4 x to the negative 3/2 power. Agreed? One reason I don't like to use the ticks with the y is because if you're sloppy, see what happens? You can't see whether that's a y or a y prime. So whenever I do it like this, I'm always trying to be very careful to make my ticks a little bit away from the y. The old phrase, cleanliness is next to godliness, very much applies in mathematics. That phrase kind of means just something as simple and as mundane as being clean is close to something as deep and profound as being godly, whatever godly means, just good or whatever, right? And similarly, you can get messed up on a problem if you're just sloppy with your notation and just aren't careful in the way you write. So that's all part of good mathematics. So anyway, let's go ahead and check it out. So what does it say? It says you take the second derivative and you multiply it by 2x squared. So let's give it a try. So 2x squared times the second derivative, which is negative 1/4 x to the negative 3/2 plus 3x times the first derivative, which is going to be 1/2 x to the negative 1/2 power minus y, and y is just x to the 1/2 power. Question is, does that equal 0 or not? So let's check it out. So if you notice, you have to know your algebra in this course. It's going to be a negative 1/2 x to the 1/2 power plus plus 3/2 x to the positive 1/2 power, because that's a 1, and then minus x to the 1/2 power. And notice that I have 3 halves of them, and here I subtract 3 halves x to the 1/2. So that's all equal to 0. So sure enough, that's a solution. So the answer to this one is yes. That one is. Okay, let's try the second one. Just for sake of space, let me erase this now. And we'll keep everything right underneath the DE. So, and I'll also erase this. And here we go. So this, of course, is the same as x to the negative first power. So when I take the first derivative, it's going to be minus x to the negative 2. Oops, I'm going to write it as y prime, just to be consistent. And y double prime is going to be what? Bring the negative 2 down, it's going to be 2x to the negative third power. Everyone agreed? So let's check to see what happens. So here you get 2x squared times the second derivative, which is 2 times x to the negative third power, plus 3x times the first derivative, which is minus x to the minus 2 power, and then minus y, and y itself is x to the minus 1 power. And let's see once what happens when we do that. Here we're going to get 4, and this is going to be, I'm going to just write that as 4 over x, because that's the same as 4 over x, and this is going to be what? That's going to be plus 3, and you multiply this by this. Oh, it's going to be a minus actually, won't it? It has a negative there, so it's going to be minus 3, and it's going to be divided by x. And then here we have a minus 1 over x. And sure enough, you factor the 1 over x out, you're going to get 4 minus 4. Sure enough, that's equal to 0. So yes, so this one is also a solution. Okay, let's try the third one. Third one says, what do? I take 2x, let's first of all take the derivatives. The derivative of x squared is 2x. The second derivative, of course, is just 2. So what does this say to do? We take 2x squared times the second derivative is going to be 2 plus 3x times the first derivative, which is 2x, and then minus the function itself, which is x squared. And let's see once what we get. So this is going to be 4x squared plus 6x squared minus x squared. Ah, too bad. Notice that's not a solution. That is not equal to 0. That's equal to 9x squared, which is not equal to identically being 0. So this is not a solution. Whoops, right here. Not a solution. Okay? So there you go. That's one example of one of the exercises from the textbook, and let you take it from there. So I guess we'll stop at that point. You know what? I'm going to go through one little note. I'm mentioning here that it's just in time with all the calculus. It's overtime if you don't know your algebra, but let me give you a quick review of algebra in case you need it. So this, or I shouldn't say algebra, but basically properties of the exponents. These two things, and I used this already in the first lecture. The exponential and the logarithm function are inverses. They undo each other. So if you were to graph each of those, exponential function looks like this. You flip it over the line y equal x. The ln function looks like this. If you start with an x here and find the e to the x, and then you take that value and you take the ln of that, you'll end up right where you began, right here. They are symmetric with respect to the line y equal x. So this thing right here is just equal to x. They undo each other. What are some other properties of e to the x? E to the x plus y is equal to e to the x times e to the y. Okay? Same as anything else, right? If you have 2 to the third times 2 to the fourth, well, that means you have this, and this means you have this. You multiply those together, and you get 2 to the seventh, right? You just add those together. So that's that one. Similarly, e to the x minus y is going to be e to the x divided by e to the y for the same reason. If you have I'll do it with 2 to the fifth divided by 2 cubed. That's 5 of them divided by 3 of them. And you end up with 2 squared, right? So you subtract the exponents. So that's true. E to the 0, just like 2 to the 0, is equal to 1. E to the x to the y power is equal to e to the x times y. And again, just apply it to something that makes more sense to you. If I take 2 cubed all to the fourth power, what does that mean? That means I have 2 cubed times 2 cubed times 2 cubed times 2 cubed. So I have 3 of them here, 3 here, 3 here, 3 here. I'm going to get 2 to the 12th, right? So I just multiply those together. Okay? Then, what are the kind of corresponding properties of the ln function, of the natural log? Again, they undo each other. So that's just equal to x. The ln of x times y is equal to the ln of x plus the ln of y. And by the way, if you want to see a proof to this, I think I prove it back in my Essentials of Calculus, Calc 1. In the first section or so, we go through properties of these functions, and so in the first few sections, and so I think I do it there if you're interested. Similarly, the ln of x divided by y is the ln of x minus the ln of y. And the ln of 1 is equal to 0. And finally, and the ln of x to the y power is y times the ln of x. Okay, so those are very important. Students often get them confused, forget what's what, but these should be easy if you just think of 2's and other numbers that you know, and then these, until you get real used to them, you just memorize them. Nothing wrong with memory. Multiplication there, you have addition there. That's pretty cool, that the ln of this times this is equal to that. In fact, one little technical problem with this kitchen calculus is that my computer freezes up on me from time to time. So it froze up right at the end there. But that was actually the end of my little review of the exponential and logarithm. And so in the following section, we are going to go on and talk about first order separable DEs, which now you should know what that term means. And we'll have lots of examples of these as we go. So see you then.